Assalamu alaikum. My name is Muhammad Saqlain. Today we will discuss about Runge kutta method order 4. First of all, introduce my topic and its contents. And the contents of my topics are introduction, second one is history, then we will move toward explanation, and there are other parts of explanation which are we are use arc method, and next one is uses states, then we will discuss about slopes, and last one is arc method solve differential equation, and then we will discuss about the example of a Runge-Kutta method of order 4, and then we will discuss about advantages and disadvantages, and then we will discuss applications. First of all, we will discuss about the introduction of Runge-Kutta method of order 4. The Runge-Kutta method of order 4 is tasked to find values of unknown function y at a given point x. The Runge-Kutta method find approximate value of y for a given x. Only first order ordinary differential equation can be used in Runge-Kutta method of order 4, and we can only solve by the method of Runge-Kutta method of order 4 only first order ordinary differential equation. The Runge-Kutta method is a numerical integration technique which provides a better approximation to the equation of motion, unlike the Euler method which calculates one slope at an interval. The Runge-Kutta calculates 4 different slopes and use them a weighted average. Now we will discuss about the history of Runge-Kutta method of order 4. The Runge-Kutta method was developed by two German men, Karl Runge 1856 to 1927 and Martin Kutta 1867 to 1944. In 1901, Karl Runge developed numerical method for solving the differential equations that arose in his study of atomic spectra. The numerical methods are still used today. He used so much mathematics in the research that physics through he was a mathematician, and he did so much physics that mathematician thought he was a physician. Today his name is associated with the Runge-Kutta method to numerically solve differential equation. Kutta, another German applied mathematician, is also remembered for the contribution to the differential equation based Kutta-Joukowski theory of airfoil lift in aerodynamics. And now we will move towards the explanation. Runge-Kutta method can be used to construct high-order accurate numerical method by functions self without needing the high-order derivatives of functions. It needs 4 value of function in each step iteration, also called 4-order Runge-Kutta method. And now we will discuss why use arc method. In numerical analysis, the Runge-Kutta methods are a family of implicit and explicit iterative methods, which includes well-known routine called Euler method, used in temporal discretization for the approximate solution of ordinary differential equation. And now we will discuss about uses states. The fourth order method is presented, which uses only 2 memory locations per dependent variable, while the classical fourth order Runge-Kutta method uses 3. Now we will discuss the important content of our topic, which is slope. Slopes plays very important role in this topic. So Now we will see what are slopes. Instead, we will restrict ourselves to the much more commonly used fourth order Runge technique, which use for approximation to the slope. Now we will discuss about Runge fourth order method to solve differential equation. And it is also lay out the Runge method of order 4. Given following inputs, an ordered differential equation that defines value of dy over dx in the form x and y. Initial value of y, that is y naught, y0, that is known as y naught. Thus we are given below dy over dx equal to f of xy, which f of xy will be given function. So we will discuss in a detail in the example what is f of xy. So y of 0 equal to y naught. The task is to find the value of unknown function y at a given point x. The Runge method finds approximate value of y for a given x. Only first order differential equation can be solved by using the Runge fourth order method. Below is the formula used to compute next value yn plus 1 from previous value yn. The value of n are 0, 1, 2, 3 and so on. X minus x naught over h. Here h is step height and xn plus 1 equal to x naught plus h. Now we will discuss about slopes. Here k1, k2, k3 and k4 are slopes. So lower step size means more accuracy. The first slope is k1 and which is equal to hf xn yn, and next slope is k2 which is equal to hf xn plus h over 2 comma yn plus k1 over 2, and next slope is k3 and it is equal to hf xn plus h over 2 comma yn plus k2 over 2, and last one is k4 and it is equal to hf xn plus h in comma yn plus k3. And the formula of Runge method is yn plus 1 which is equal to yn plus 1 over 6 into k1 plus 2 k2 plus 2 k3 plus k4. The formula basically computes next value yn plus 1 using current yn plus weighted average of 4 increments. And now we will discuss about what are k1, k2, k3 and k4. Basically k1 is the increment based on the slope at the beginning of the interval using y, and k2 is the increment based on the slope at the midpoint of the interval using y plus hk1 over 2. And the third slope, which is known as k3, k3 is again the increment based on the slope at the midpoint using y plus hk2 over 2. And the last slope which we will use in the formula, which is equal to k4. k4 is increment based on the slope at the end of the interval using y plus hk3. The method is fourth order method, meaning that the local truncation error is on the order of 0h power 5, while the total accumulated error is order 0h power 4. Now we will move towards our example, and example is here. Using RK method of order 4, solve dy over dx, and given function is y square minus x square over y square plus x square with the condition which are known as initial condition y0 equal to 1 at x equal to 0.2 and x equal to 0.4. So given function here fxy equal to y square minus x square over y square plus x square, and given x not equal to 0 and y not equal to yx not equal to 1. Here h is equal to 0.2, and h plays very important role in this example because our number of steps are depend upon the value of h. So we want to find the value of 0.2 and 0.4, and we can take h 0.1 and then we can find 0.1, 0.2, 0.3 and 0.4. But if we choose 0.1, then our steps will be 4, and it is a long process, so we will take h equal to 0.2, so our number of steps will be 2 because we want to find 0.2 and 0.4. And now we will discuss about x1 equal to x naught plus h, and x naught here equal to 0 and h equal to 0.2, so x1 equal to 0.2. And here we will use only x naught and x1 values, and we will find the value of x2 only for our understanding how to find the next values. So x2 equal to x1 plus h, x2 equal to, and we know that x1 equal to 0.2 plus h is equal to 0.2. So by substituting the value of x1 and h, we can find the value of x2, which is equal to 0.4. Now to find y 0.2, which is equal to y1, and y 0.4, which is equal to y2. So we already choose h equal to 0.2, that's why our number of steps will be 2. And when we will take x equal to 0.2, then it is equal to y1, and which is known as step 1, and when we choose 0.4, it is equal to y2, which is our second step. By using Runge kutta method order 4, here we can see the formula of RK method of order 4. yn plus 1 equal to yn plus 1 over 6 k into k1 plus 2 k2 plus 2 k3 plus k4. And now we will find the value of k1, k2, k3 and k4, and also we will find the value of yn, and we will substitute the values into the formula, and which is our required solution. So we know that where k1 is slope 1, and it is equal to hf xn yn, and also k2 is second slope hf x2 plus h over 2 comma yn plus k1 over 2, and our third slope, which is known as k3, and it is equal to hf xn plus h over 2 comma yn plus k2 over 2, and our last slope, which is k4, and it is equal to hf xn plus h comma yn plus k3. And now we will move towards our first step, and here we substitute the value of n equal to 0 into RK method formula. Here we will substitute y 0.2, which is equal to y1, and when in the formula we will substitute the value of n equal to 0, then our formula will be look as y0 plus 1 over 6 k1 plus 2 k2 plus 2 k3 plus k4, and we are also know that y0 is equal to 1, so our remaining variables are k1, k2, k3 and k4. And now we will find the values of k1, k2, k3 and k4, and we will substitute in our formula. Then we can find y1, which is our solution. And here k1 is equal to hf x naught y naught, and the first value will be x naught and second value is y naught. And we know that the value of h is equal to 0.2, and we will put into our function, which is equal to y square minus x square over y square plus x square. When we will substitute the values of y square minus x square, we can find k1 is equal to 0.2. Now we will find our second slope, which is equal to k2, and which is equal to hf x naught plus h over 2 and y naught plus k1 over 2. Here we know about the value of h, and also we know that the value of x naught, which is equal to 0, and already we know about the value of h, and y naught is equal to 1. And first of all we find the value of k1. Already we derived the find the value of k1, and here we can substitute the values of all the variables, so we can easily find the value of k2, and the same function will be used here. And now we will move our next step, which is equal to k3, and now we will find the value of k3, which is equal to hf x naught plus h over 2 into y naught plus k2 over 2. And we know the value of h and x naught, also y naught and k2. So we will substitute the values of h, x naught, y naught and k2 in the given formula. From here we can find the value of k3, which is equal to 0.1967. And now we will find our last value, which is k4, and k4 is equal to hf x naught plus h, y naught plus k3, and all the values we have. So by substituting the value of h, x naught, h, y naught and k3 in the given formula, so the value of k4 is 0.1891. Now by all the values which were our required values, we are already find. So now by putting the value of k1, k2, k3 and k4 in y1, now we will substitute the value of y1 equal to y 0.2, which is also equal to y1, and here the value of y naught is equal to 1 plus 1 over 6, and the value of k1 is equal to 0.2 plus 2 into 0, value of k2 is equal to 0.19672 plus 2 into the value of k3, which is equal to 0.1967 plus the value of k4, which is equal to 0.1891. And the final solution, our y1, which is equal to 1.19599. Now we will move our second step, which is known as step 2. Put n equal to 1 into arc method formula. Here the formula will be look as y2 is equal to 0.4, which is equal to y1 plus 1 over 6 into k1 plus 2k2 plus 2k3 plus k4, where k1 equal to, and the slopes will be remain same, but the values will be changed here. Now k1 equal to hf x1 into y1, because here the value of n is equal to 1. So by the substituting the values of x1, y1 and h, our k1 will be equal to 0.1891. Now we will find our second slope, which is K2. uh, K2 is equal to HF x1 plus h over 2 comma y1 plus k1 over 2 equal to 0.1795. And now we will find the value of K3. K3 is equal to HF x1 plus h over 2 comma y1 plus k2 over 2. And we know the values of h, x1 and y1 and k2, and we will substitute this value and we can find the value of k3, which is equal to 0.1793. And now we will find our last value, which is k4, and k4 is equal to hf x1 plus h comma y1 plus k3. And we know the value of h and x1 and y1 and k3. By the substituting these values, we can find the value of k4, which is equal to 0.1688. Now we already find all the values which were required. So by the substituting the values of k1, k2, k3 and k4 values into y2, here y2 equal to y into 0.4 will be equal to y1 plus 1 over 6 k1 plus 2 k2 plus 2 k3 plus k4. y2 equal to y 0.4 equal to 1.96 plus 1 over 6, and the values of k1, k2, k3, k4 we can substitute in this formula, and we can find the value of y2, which is equal to 1.3752. And now we will move towards our next content, which is advantages and disadvantages. First of all, we will discuss our advantages, then we will move towards disadvantages. Advantages are Runge kutta method are based on using higher order term of Taylor series expansion, one of the most widely used and efficient numerical integration method is fourth order Runge kutta method. And the next one, it is simple to implement and yields good numerical behavior in most applications. Also, it is generally recommended over Euler integration. They are stable. And now we will discuss the disadvantages. And such algorithm may take numerous computation time. They do not work well for stiff differential equation. This is more expensive than Euler integration. And now we will discuss about the application of Runge kutta method of order 4, which is equal to when sending a satellite to another planet, it is often necessary to make a course correction midway. The differential equation governing the motion are well known, so the projected path can be calculated by solving the differential equation concerned. Often this is done using a Runge kutta method or a variant theorem, particularly if the effect of another planet is of consequence. Likewise, if a correction has to be made, the effect of correction, again a Runge kutta technique can be used. So thank you.